Yeah, hello guys. So today we are going to run through one of the building blocks of digital electronics, the flip-flops. These tiny circuits, are crucial in storing and processing data. So what exactly is a flip-flop?
A flip-flop is like a tiny memory cell that stores a single bit of data, either 1 or 0. It is controlled by clock signals, which then acts as a metronome to tell it when to update.
And there are several types: RS, gated RS, JK, and the star of our discussion today, the D flip-flop.
Alright, perfect. So by the end of this, we will understand what the D flip-flop is, how it works, and why it's so widely used in digital systems. So let's start with the basics.
Flip-flops are sequential circuits, unlike combinational circuits, which depend only on inputs. Flip-flops depend on both inputs and their current state. This makes them perfect for storing data.
They are controlled by clock signals. When the clock ticks, the flip-flop either updates its state or holds onto the current one. This synchronization is crucial in digital systems.
And among all the flip-flops, the D flip-flop is one of the simplest and most reliable. It's the focus of our discussion today. Ready to dive in? What is a D flip-flop? The D in D flip-flop stands for data or delay. It has a single data input, D, a clock input, and two outputs, Q and Q bar. Its purpose: to store the value of D at the moment the clock signal ticks.
Okay, so let's think of it this way. When the clock's rising edge occurs, the D flip-flop captures the value of D and outputs it through Q. Between clock pulses, Q remains constant.
This ability makes it incredibly useful. It ensures that output changes are synchronized with clocks signals, eliminating ambiguity in data storage.
Let's look at the truth table. When the clock ticks, Q output mirrors the D input. If D is 1, Q becomes 1. If D is 0, Q becomes 0. In between ticks, Q holds its previous value.
The timing diagram shows this visually. When the clock transitions from low to high, Q changes from match D, otherwise it stays the same, even if D fluctuates. This behavior is what makes it D flip-flop predictable.
Let's animate this with an example. Imagine the D input changes as 1, 0, 1, 1 while the clock ticks. The Q outputs will follow this pattern only at the clock edges, ignoring any changes in between.
Internally, the D flip-flop is built using the NAND gates or NOR gates. Essentially, it modifies RS flip-flop with additional logic to prevent invalid states.
In advanced designs, a master-slave configuration is used. This involves two flip-flops in series. The master captures data on one clock edge, and the slave locks it in on the next. This ensures even greater stability.
So, where is the D flip-flop used? Pretty much everywhere. Shift registers, counters, memory elements, you name it.
For example, in a shift register, multiple D flip-flops are connected in series to store and transfer data bit by bit, like passing a baton in a relay race.
Another example is a frequency divider. By feeding the output back to the input through an inverter, the D flip-flop can halve the clock frequency, creating timing signals.
Of course, no design is without its challenges. D flip-flops can also face timing issues, like also setup and timing code, time valuation. This happens when the input is unstable, long enough before or after the clock pause.
But with careful design, these issues are manageable. The advantages, simplicity, stability, and versatility makes the D flip-flop indispensable in digital circuit.
Alright, so in wrapping up, or to sum up everything, we are going to say that the D flip-flop is a fundamental component of digital systems. It is simple yet powerful, ensuring data is stored and synchronized accurately. Absolutely. Whether it's memory chip, a counter, or a register, the D flip-flop plays a key role. Thanks for tuning into our discussion. Thank you.